Welcome back, class 12. In the last class, we were discussing about elimination reaction, E1 and E2 reaction, and we had also seen Wood's reaction. Today we will take up the difference in reactivity of haloalkanes and haloarenes. Difference in reactivity of haloalkanes and haloarenes. Under that, first is difference in the nature of carbon. Let us take a haloarene. This is undergoing resonance. You can see the minus I effect of benzene ring pulls the electron towards itself, and we get different resonance hybrid structures. Thereby, the electron is being shifted throughout the ring, and at the end, the electron comes back to its original position. We see here there are 5 resonating structures, and we can see that the carbon here is acquiring a double bond. A double bonded carbon atom means that the carbon is sp2 hybridized. Let us take an example of haloalkane. See, this is an example of chloromethane. This carbon has got 4 bonds. Here we can see that this carbon is sp3 hybridized. This clearly indicates that the double bond character of this carbon makes it difficult to break the bond. That means that when we compare the reactivity of a haloalkane and a haloarene, we would say that haloalkane is more reactive because it is consisting of an sp3 hybridized carbon atom, whereas a haloarene consists of an sp2 hybridized carbon atom. And it is difficult. We know that a double bond means there is one sigma bond and there is one pi bond. So it is difficult to break this bond. Thereby, the reaction here is slower, or we can say it is weaker. Now, when we talk about reactivity here, let us take up first the nucleophilic substitution reaction in haloarenes. Let us take it one by one. Haloarenes react with sodium hydroxide in presence of, say, 643 Kelvin and in presence of H+, gives phenol. Also, if a nitro group is present here, the reaction requires less heat, say 443 Kelvin, in presence of H+, to give the substituted product. Also, if there are two nitro groups present here, the reaction would all the more require less heat in presence of H plus to give the substituted product. If we have three nitro groups present, the reaction would require only heating up, little bit of warming up, three nitro groups present here, so we require little bit of warm up in presence of H plus to give 2,4. Let us number it. 1, 2, 3, 4, 5, 6. 2,4,6 trinitrophenol. So we see here that the nucleophilic substitution reaction is a bit difficult in this case. Let us see electrophilic substitution reaction. Electrophilic substitution, as the name implies, means attack of an electrophile. Electrophile is electron loving species. That means this would look for a negative charge anywhere in the vicinity of the reaction. So whenever an electrophile comes, that means it would look for a negative charge anywhere in the reaction substrate. So we had already seen when we had drawn the resonating structure of a haloarene, we had seen, I'm drawing it again. Here we can see when we are drawing the resonance hybrid, you can see that the negative charge is coming either in the ortho or in the para position. This electron shifts here and you can see this electron comes in the ortho as well as in the para position. You can see this is ortho, meta, para, ortho, meta, para. So here at ortho position we are getting a negative charge. Here at para position we are getting a negative charge. And again in the ortho position we are getting a negative charge. That means whenever the electrophile would come and attack the substrate, it would always take place either in the ortho or in the para position, never at the meta position, because this position is electron deficient. There is no electron present in the resonance when we make the resonance hybrid of a haloarene. So let us take up the first type of reaction here, that is nitration. Nitration means the addition of the nitro group. Say in presence of HNO3 and H2SO4, the reaction is proceeding. We get two products. The substitution in the ortho position and the substitution in the para position. Similarly,